In this lesson, we will be talking about functions. Specifically, we'll talk about relations and functions, their differences. We'll talk about domain and range, determining whether or not relations are functions. We'll introduce function notation, and we'll also talk about the concepts of increasing, decreasing, and constant. First of all, let's define a relation. A relation is simply a set of ordered pairs. So we write sets of ordered pairs in braces. So for example, we may have the set of ordered pairs 1, 2, -3, 5, 4, 10, and so on. And so we denote a set of discrete points using these braces to denote a set. All right, and then going on to talk about a function. A function is a relation for which each distinct value of the first component of the ordered pair has exactly one value for the second component. In other words, every x value is paired with exactly one y value. So therefore, with functions, you have no repeating x values. So, a relation would be any set of ordered pairs with no restrictions, whereas a function does have a restriction on the ordered pairs. You can't have any of the x values repeating. So let's now take a look at some examples. First of all, we want to decide whether this relation defines a function. Clearly it is a relation because it is a set of ordered pairs. Now for this relation to define a function, we cannot have any repeating x values. And so here, all of the x values are different, and therefore this relation is a function. Let's look at another set. So here, in this set of ordered pairs, it is a relation because every set of ordered pairs is a relation. However, this relation is not a function. We know that it's not a function because we have the x value of 1 repeating. It's being paired with multiple y values. Okay, one more. The function, or the relation, I should say, that's given here is the set of ordered pairs -4, 1, -2, 1, and -2, 0. Like the last example, because these x values repeat, then we do not have a function. -2 is being paired with both 1 and 0, which makes this relation not a function. Now I do want to take a moment and say something about the y values. It is okay for the y's to repeat. That has no bearing on whether the relation is or is not a function. There is a significance that we'll explore in a different lesson about repeating y values, but in terms of relations and functions, y's are not a determining factor. Okay, and so we want to take a look now at a different way to represent relations and functions. So instead of representing relations and functions as set of ordered pairs written with the braces, we can represent those ordered pairs as mappings. And so we put all of our x coordinates here, and we put our y values here, right? And so we have our ordered pairs then represented here in these ovals. So 1 is being mapped to 2. So that is the same as the ordered pair 1, 2 if we were to rewrite this in this set notation. -2 is being paired with 4. 3 is also being mapped to 4, okay? So as we can see here, none of the x values repeat, right? So they're all different, and even though we have a repeating y value, we know that that has no relation or impact on whether or not this is a function, right? So here we have, yes, f is a function. However, in H, right, in that relation that we see to the right, we see here repeating X values, right? Because we have -2 that's being mapped to two different Y values. So if we were to write this relation as a set of ordered pairs, we would have -4, 1, -2, 1, and -2, 0. Okay? So we can see clearly here when we write it out as a set that our X values do repeat. So with mappings, you cannot have the same X value being mapped or sent to two different Y values. Okay, one note about relations is that we can think of this function relationship as an input and output. And so if we think about our function f as being a machine, then what we're doing here is we're inputting X values, right? And then our function f is performing some function, some alteration of X, and then we're outputting a Y value. Okay, so again, you can think of functions as kind of a machine. Okay, next we're going to talk about a very important concept, the concept of domain and range. Okay, and this concept of domain and range is used throughout pre-calculus. Okay, and so the set of all X values is called our domain. Okay, so the set of all X's is the domain. The set of all Y, y values is our range. So let's look at an example. Let's determine the domain and the range. So we said a moment ago that the domain consists of all the X values. Therefore, our domain would be the set containing 3, 4, and 6. 4 is repeating, so I do not need to list that twice. I can just list that once. Okay. For the range, now we're going to look at the Y values. So all of the Y values comprise the range. So we list them, -1, 2, 5, and 8. We notice that this relation is not a function because we have repeating X values. We have 4 that's being paired with both 2 and 5. And we can't have any repeating X values. So no, this relation is not a function. Okay, another example. Here we are given the domain and range represented as a mapping. Okay, and this relation does define a function. So yes, okay, this relation is a function. Okay, and the reason that it's a function, as we said before, is because the X values are not being mapped to multiple Y values. Each X value is paired with exactly one Y. So we've looked at two other ways to represent relations and functions. That is a set of discrete ordered pairs. We've also looked at relations and functions as mappings. We can also think of relations and functions in terms of a table, right? So we can put our ordered pairs in a table and represent the relation or function that way. So this table is analogous to -5, 2, 0, 2, and 5, 2. Okay. Because there are no repeating X values, then that relation does define a function. Our domain consists of -5, 0, and 5, and our range would consist of the 2 only. Okay, so we would write our domain as the set containing -5, 0, and 5, and the range would contain one element, 2. Okay, and so now let's talk about a third way to represent functions and relations, and that is given a graph. Now, sometimes a graph contains just ordered pairs, and they are not connected in any way. They're just a discrete set of ordered pairs. In that case, we represent our relation here as a set of ordered pairs. Okay, so negative 1, 1, 0, negative 1, 4, negative 3, and finally 1, 2. Okay, it does not matter what order we list them in, right? We just, it's a listing, so order does not matter. We're asked to give the domain and range, so the domain would be all the x values. That is the set containing negative 1, 0, 4, and 1. Again, order does not matter. I could have written 1, 4, 0, negative 1. The range is the set containing 1, negative 1, negative 3, and 2. Notice we're not asked to determine whether this is a function or not, and we'll take a look more at that in a moment. Okay, and so sometimes our graph has ordered pairs that are connected in some way as a continuous graph. And so here we have a figure whereby we're asked to determine the domain and range. The domain is the set of all x values. So I look left to right from negative infinity to infinity, and I look at where my graph is defined. So I know that I have no x values over here. The graph starts at negative 4. All right, and then as I continue right, I see that for all the x values between negative 4 and 4, I have corresponding y values somewhere on the graph. So all of these are ordered pairs, and there are infinitely many of them. All right, and then as I move to the right of 4, there is no graph over there. So my domain would be all the values from negative 4 to 4. Now I'm going to express this domain in interval notation. I do that because there are infinitely many ordered pairs between negative 4 and 4 that would be on the graph of the relation. Likewise, for the range, I will look from negative infinity to positive infinity and look at what values my relation in this case can take for y. So I have negative 6 all the way up to positive 6. Again, I'm including those the lowest and the highest value, my negative 6 and 6, using brackets because those are points on my graph. Okay, next we'll look at this line. So the domain and the range are one and the same. All right, you can see that this line continues infinitely left to right. I know that because of the arrow tips on the ends of the line. And so therefore my domain is all real numbers. Okay, and likewise my range is all real numbers. Okay, for this graph, I see that my domain is made up of all real numbers, negative infinity to infinity. That might be a little more difficult to see. You might be inclined to just, shorten that and include only the parts of the domain, the x values that you see, right? But you have to imagine that this graph is going to continue infinitely upward, and so eventually that's going to encompass all the x values. All right, the range. For the range, we're going to look bottom to top. We notice that there is no graph down here, right? The graph does not start until y is 3, and then it continues infinitely upward. So our range would be negative 3, so negative 3 on up to infinity. Notice that negative infinity and infinity cannot be captured, so there's always parentheses that are used there. Okay, and so next we'll talk about the vertical line test. If we're asked to determine whether a relation is a function, we can simply draw a vertical line. So if the vertical line meets the graph, in at most one point, then that relation is a function. If you can find a vertical line that meets the graph in more than one place, then the graph is that of a relation, but it's not a function. Okay, so here, if we're asked to determine whether the relation is a function, we can see if there are any vertical lines that meet the graph in more than one spot. So clearly, I draw a vertical line. It meets in one spot, here one, here one, here one. So by the vertical line test, this graph, this relation is also a function. My next graph, if I use the vertical line test, because I can find a vertical line that meets the graph in more than one place, then this relation is not a function. And so there are multiple vertical lines that could demonstrate this, okay? But all you have to do is find one. If you can find one vertical line that meets the graph in more than one place, then the graph is not a function. Okay, and so here we're going to consider this relation, and so this graph passes the vertical line test because every vertical line drawn meets that graph in just one place. So this relation is a function. Okay, and we'll continue on and do a couple more examples. So here, this relation is a function by the vertical line test because our vertical lines meet the graph in at most one place. Okay, and so here we want to decide whether we have a function and we want to give the domain and the range. So here I have a graph in two variables, or an equation, I should say, in two variables. So we can simply imagine what our graph would shape up to be if we let x take on certain values, okay? And so as we do that, we would get a line. So y equals x plus 4 is a line that has a y-intercept of 0, 4. And so we looked at an example of a line earlier. The domain is negative infinity to infinity. Same thing for the range. And this is a function by the vertical line test. Okay, moving along. So here we have y equals the square root of 2x minus 1. One way to tackle this problem would be to graph it, right? If you do not know what the graph looks like, you can rely on algebraic methods. We know that the square root will have to be positive underneath. That quantity under the radical would have to be non-negative because we can't take the square root of a negative number and be in the real number system. So the quantity under the radical, which is 2x minus 1, has to be greater than or equal to 0. So we solve that. So we have 2x is greater than or equal to 1, and then x is greater than or equal to 1/2. Okay, and so here as we plug in various values of the domain, we have here the smallest that y can be would be 0, and that's in the case that x is 1/2, and then it would continually grow bigger from there. So our domain is 1/2, comma, infinity. Our range is going to be 0, inclusive, comma, infinity. And this relation does define a function because there would be no x's that repeat. Okay, and so next we're going to look at variations of the definition of a function. Okay, so a function is a relation in which for each distinct value of the first component, there's exactly one value of the second component. Alternatively, a function can be defined as a set of ordered pairs in which no first component is repeated. A third way to say it would be that a function is a rule or correspondence that assigns exactly one range value to each distinct domain value. Okay, we also want to talk about function notation and finding an expression for f of x. So consider an equation involving x and y, okay? If we want to find an expression for f of x, we can just solve the equation for y and replace y with f of x. For example, let's say we have y equals x squared plus 1. Okay, so we're going to assume that y is a function of x. If we want to rewrite that equation using function notation, we simply replace y with f of x because the equation is already solved for y. Next, we're asked to evaluate our function at -2. Okay, so we can simply replace x with -2. Simplifying, we have 4 and 1, which will make 5. And then we have f of p. So in place of x in our function, we want to replace that x with p. So we have p squared plus 1. Okay, finally, the last thing we're going to talk about is the concept of increasing, decreasing, and constant. So it's very intuitive. Increasing means that you have a rise from left to right. Decrease means that you are falling left to right. Constant means no change. So here, looking at this example, we see that our function going from left to right, it's decreasing from -infinity to -2. Okay, notice that my function, my increasing, decreasing, and constant is described over values of the domain. Okay, so it's decreasing from -infinity to -2. All right. And then it is going to be increasing on the next interval from -2 up to 1. So it's increasing from -2 to 1. And then finally, it is constant for the remaining portion of the graph. So it is constant from 1 to infinity.